So as we get into our module 14, and we're taking a look at the topic of our energy methods. So within this module, we're going to introduce the concept of strain energy. Now this is going to be the increase in the internal energy associated with the deformation of the member. Now the strain energy is equal to the work done by slowly increasing the load applied to the member. Now we're also going to introduce the elastic strain energy associated with the normal stress for the members under axial loading and in bending. Now, upon completion of this module, you should be able to compute the strain energy due to axial, bending, and torsional loading. We'll discuss all three of those. Determine the effect of impact loading on members. Define the work done by a force or a couple. Then we're going to look at determining the displacements from a single load using the work energy method. Then we're going to apply Castigliano's theorem to determine displacements due to multiple loads, not just a single loads. And last, we're going to solve statically indeterminate problems using Castigliano's theorem. So relating back to our textbook, we're going to break this down into two different sections within our module. The first section of our module is going to deal with Chapter 11 in the textbook, sections 1 through 3. And the second part of our module is going to deal with Chapter 11, sections 4 through 9 in your textbook. So for Module 14, we're going to be breaking this into two different sections, Module 14.1 and Module 14.2. For our Module 14.1, we're looking at our energy methods, in particular looking at our strain energy. Now, objectives within this module, as we're talking about our strain energy, we're going to be looking at our strain energy concepts and strain energy density. Then we're going to take a look at our elastic strain energy, breaking it down into our normal stresses and shearing stresses. And our last topic we're going to look at is our strain energy for a general state of stress. Now for activities within our Module 14.1, we're looking at the theory for the above topics, talking about our key equations, looking at our practical applications, and then going through my hand solutions to an example problem. So now let's take a look at our topic of strain energy. So for strain energy, let's consider a diagram that we see here for a uniform rod subjected to a slowly increasing load. So we have our initial rod right here. This is going to be a uniform rod from B to C. And we can see it, this one here has a length initially of L. Then we're going to apply a load. So this load P is going to be our slowly increasing load. So with this, we want to take a look at our elementary work. So elementary work is going to be done by the load P, so our load P right there, as the rod elongates by a small dx. So this is going to be given by our equation down here that du, our elementary work here, is equal to P times dx. Now, if we consider our load deformation diagram, this is going to be equal to the width, the area of the width, dx, under the load deformation diagram. So the area of the width right there is going to be dx times p, which is exactly what we have in this equation here. So the shaded area in here for our dx times p, this is going to be that elementary work. Now from there, what we can do is we consider our total work, and this is going to be the total work done by the load over the deformation to x1. So this is our distance x1 as we reference back to this load deformation diagram here. And for this, we have the governing equation that u, or the complete area under this curve here, so if we go under this whole curve here, from our point O over here all the way out to this x1, this deformation of x1 here, under our load displacement curve, our px curve right here, which is also our load deformation diagram, this is going to be equal to, says now our u is equal to the integral, which is the area under a curve, from 0 to that x1, so from 0 to that distance x1 of p dx. Now this is going to be the total work, or what's also known as our strain energy. And this is because this results from the increase of the strain energy in the rod. So now we want to consider the case for linear elastic deformation. Now for this, we have the governing equation that we see here, that u is equal to the integral from 0 to x1 of kx dx, which is equal to 1/2 kx1 squared when we do out our integral right there, which is equal to now 1/2 p1 x1. So then we can come down to our diagram here for work due to linear elastic deformation. And we can see this, our u is the area under the curve from our 0 to x1, just as we see in our integral, because our integral is going to be the area under a curve. And this goes up to our distance right here, p1, where we end this right here. So then we can see there is that equation that u is equal to 1/2 p1 x1. Now if we think about that right there, what is an area of a triangle? 1/2 base times height. So that's exactly the relationship we have here. So we have 1/2, we have our height p, and we have our base x1 there. So that is the area of a triangle, which is the area under a curve here, defined by this integral. So as we talked about earlier in this course in our textbook, the load deformation diagram for that rod BC is going to depend upon the length L and its cross-sectional area A. Now our strain energy, this U term, is defined by our equation that we see here, this 11.2 in our textbook, where U is equal to that integral from 0 to the length out here of x1 of px dx, which is going to be our total work or our strain energy. So with that and what we saw earlier in the book, we can now say that the strain energy U is also going to be dependent upon the dimensions of the rod, that L, and our cross-sectional area A. Now, if we wanted to eliminate the effect of size and instead direct the attention to the properties of the material, then the internal strain energy per unit volume could be considered. The way we can do this is we can divide that strain energy, our U, by our unit volume right here. So we divide this by volume right here, and for a rod, our volume is equal to AL. So that's where we come up with this relationship that we see here. If we take that strain energy and divide by our volume, this is going to be equal to the integral from 0 to our x1 of P over A times dx over L. So our total strain energy density resulting from deformation is going to be equal to the area under our curve up until this point of our epsilon 1. So we come over here to our diagram. This is our typical stress strain curve. There's our strain on our x-axis, our stress on our y-axis, and this is our epsilon 1 that we're talking about here, which is going to be where we're going our area up to, and we can see that in this curve here. This curve shows the strain energy density is equal to the area under the stress strain curve between epsilon sub x is equal to 0 down here, and epsilon sub x is equal to our epsilon 1 here. So if loaded into the plastic region, only the energy associated with the elastic unloading is recovered. Now what this is saying is that as the material is unloaded, the stress is going to return to 0, but there is a permanent deformation. So only the strain energy represented by the triangular area right here that we can see, this darker shaded area, is going to be recovered. The remainder of the energy spent in deforming the material is going to be dissipated as heat. So this then gives us our governing equation for our strain energy density. You can see I've boxed this in here in red. This relates back to our equation 11.4 in our textbook, where we have our U, or our strain energy density, is equal to the integral from our 0 to epsilon 1, from our 0 to our epsilon 1 here, as we relate this back to our graph over here for our strain energy density. And this is going to be the integral of our sigma x d epsilon x. So this again is our governing equation for our strain energy density from equation 11.4 in our textbook. So as we continue on with our topic of our strain energy density, let's consider the case where epsilon 1 is equal to our epsilon r. So for this case, the strain energy density resulting from setting epsilon 1 equal to epsilon r is what's known as our modulus of toughness. So we can take a look over here at our diagram on the left, and the modulus of toughness is the area under the stress strain curve up to rupture. So you can see that epsilon sub r occurs, that's our strain, at our rupture point here in our stress strain curve. And we can see that area, the shaded area here, we've denoted on this chart here as our modulus of toughness, so that area under that curve. So now the energy per unit volume required to cause the material to rupture is going to be related to its ductility as well as its ultimate strength, which is information that we can get from our stress strain curve. Now with this, if our stress is to remain within that proportional limit of the material, so we can see our proportional limit of the material on our stress strain curve over here, then we have the relationship that we see in our equation 11.5, where our sigma sub x is equal to our modular elasticity times our epsilon sub x. That's just basically rearranging Hooke's law to come up with this relationship we see here in 11.5. Now for our energy, we can move to our equation 11.6 and 11.7, where we see that U is equal to that integral from 0 to our epsilon 1, which is going to be the area under the curve, starting at our point 0 all the way up to that epsilon 1, of our modular elasticity times epsilon sub x d epsilon sub x. So we do out that integral, do out the calculus there, what it ends up being is our modular elasticity times our epsilon sub 1 squared over 2, which we can then sub into here, and we can have the relationship from 11.5, and we plug that in, that we now have what we see as our equation 11.7, that U is equal to our sigma 1 squared all over our 2 times the modulus of elasticity. Now, rather than the modulus of toughness, if we want to discuss our modulus of resilience, the strain energy density resulting from setting our sigma 1 is equal to sigma y, this is known as our modulus of resilience. So we can come over here to our curve and see the modulus of resilience is the area under the stress strain curve to yield. So that's what our epsilon sub y is this is a location here when we go up to our yield strength right here, our sigma sub y, this is our point y there, and this area under the curve here is going to be our modulus of resilience. So we can come down here and we have a general governing equation that we can use for this. Our u sub y is equal to our sigma sub y squared over 2e, which is just another version of our 11.7 equation, but plugging in sigma y for our sigma 1. So this is our governing equation from 11.8 in our textbook, that our modulus of resistance is equal to our sigma y squared over 2 times our modulus of elasticity. So previously we looked at rods that were only subject to uniformly distributed stresses, or sigma x. So the strain energy density was constant throughout the rod and could be defined by that ratio of our u over v, of the strain energy being u and the volume being v of our rod. So what about the case where we have a non-uniform stress distribution? Well, in that case there, our strain energy density, or our U value that we're seeing up here, can be defined by considering the strain energy of a small element of material of a volume delta V. So therefore, we have the relationship we see here from our equation 11.9 in our text. So we have that u is equal to our limit as our delta v, right? There's a delta v we're discussing right there, approaches 0, of our delta u over delta v. We do that limit out, we end up with du over dv. We solve this now, do out some integration. Du equal to dv there with this, u is equal to du dv. We can move our dv over to the other side, so we have u dv is equal to du. Integrate both sides of that, so we get our u. U is equal to the integral of u dv, which is going to be our total strain energy. And this goes back to our relationship that we saw in equation 11.9 in our text. So now if we're within a proportional limit and our value of u is less than u sub y, we then have our governing equation 11.12 in our textbook, where our elastic strain energy, our u, is equal to the integral of our sigma x squared all over 2 times our modular elasticity dv. So with this equation here and this relationship from 11.12, let's consider the case that we have axial loading. So we'll go up top here to our diagram on the left. We have a rod with that central axial loading right here. So for this case here, we can see that our sigma x from our equation 11.12 is going to be equal to our p over our a value there, and our dv is going to be equal to a dx. So with that there, we then have our relationship we see in equation 11.13, that our elastic strain energy, our u value here, is the integral from 0 to L, where L is the length of that rod right there, of our p squared, our load squared, all over 2ae, there's our a, and our modular elasticity e, dx. So this is for this rod that we see in the top left. But we also have the case where we might have a uniform rod, a rod of uniform cross-section, which is the case down here on the bottom left, a prismatic rod with a central acting load. We can see that this is uniform there. So now our equation 11.13 can be simplified down to 11.14, where we have our strain energy is equal to that load P squared times that length L, all divided by 2 times our cross-sectional area times our modulus of elasticity. So we can see the difference right here. This one is just for this uniform rod, where if we're dealing with this shape up here, then our area is going to change. We're going to have this integral right here when we're dealing with a shape similar to what we have in our top left for this diagram. So now let's consider strain energy in bending. So if we're looking at our strain energy for normal stresses with bending, we have this diagram for a transversely loaded beam up here on the top left. So if we consider this beam AB, so there's our point A and our point B right there, and this is going to be subjected to a given loading. So we can see our loading, we have a distributed load here, point load here, and distributed load over here. And we let M be the bending moment at a distance x away from end A here. So this will be our distance x away from our A there. Now with this, what we're going to do is we're going to neglect the effect of shear and take into account only the normal stresses. So we're going to utilize this equation here for our normal stresses, that our sigma sub x is equal to our moment m times y all over I. Now what we can do with this is we can come up here. So for a beam subjected to a bending load, we have this relationship here from equation 11.2, where u, our strain energy, is equal to the integral of our sigma x squared all over 2e dv, which we showed previously within this module. But now we have a relationship for our sigma sub x. So our sigma sub x, for this case here for our bending beam, is equal to m y over I. So we can plug that in for our sigma x squared there. And we do that, what we end up with is that our strain energy u is equal to the integral of our m squared y squared all over our 2ei squared dv. So now if we were to set our dv equal to dA dx, where our dA is going to represent an element of cross-sectional area, So that's what our dA is right there. And now we can recall from our equation above, where we have this integral over m squared y squared all over 2ei squared, that the m squared all over 2ei squared, this is going to be a function of x alone. So what we're going to do is we're going to break this into two different integrals here. So we can now say, well, we have the double integral, u is equal to, which is our strain energy, the integral from 0 to L, and the integral over a of this whole function right here, m squared y squared all over 2ei squared. But then we'll separate this out into two different integrals here. So we'll break this apart, and this will be the integral from 0 to L of our m squared all over 2ei. So this again is going to be the function of our x right there, times now the integral over a of our y squared dA. So we broke this down. Our y squared went with our dA, and our m squared all over 2ei squared went with our dx right here. So now we have this relationship here, which we can do out the math on this here, and we find out this simplifies down to equation 11.15, which is the integral from 0 to L of our m squared all over 2ei squared dx. Now let's instead consider the case of a cantilever beam with a load P. So here was our cantilever beam. This is our fixed end at B, has some total length L. Then out here at point A, at that length L, we have this load P. So this is going to be an end-loaded cantilever beam. So our moment is going to be equal to our force times our perpendicular distance, or our P times that distance L right there. Again, pay attention to your sign conventions. This will be negative Px. Then we have our strain energy equation now is going to be given by this relationship here. We have the integral from 0 to L of that load P squared times that x squared all over 2ei dx. We do out our calculus there, and this ends up being that u is equal to P squared times L cubed all over 6ei for the case of an end-loaded cantilever beam. So now previously we discussed our internal strain energy due to our normal stresses. Well, similarly, when a material is going to be subjected to plane shearing stresses, our tau xy that we see here, the strain energy density can be given by the following relationship that we see down here now, 11.16. So for materials subjected to a plane shearing stress, our u is going to be equal to our integral, with our limits here from 0 to our gamma xy, where gamma xy is our shearing strain corresponding to our shear stress that we can see over here in our diagram. And this is going to be of our tau xy d gamma xy. So this is our equation 11.16, which gives us our u value for a material subjected to this plane shearing stress. So now with this relationship, one thing that we do want to note here is that our strain energy density, our U value here, is going to be equal to the area under our shearing stress strain diagram. So this is our shearing stress strain diagram in part B of our diagram on the left. So shearing energy density, U, is going to be this area underneath the curve right there. So we can see this shaded area here underneath that curve. This is going to be our strain energy density, or our value of U. Now for the case where our values of our shear stress here, our tau xy, are within our proportional limit, so if they're in this proportional limit on our graph over here, then we have the relationship that our strain energy density, our U value, is equal to 1/2 our modulus of rigidity times that shearing strain gamma xy squared, which this can reduce down now to 1/2 our tau xy times our gamma xy, which then we can rewrite over here in this relationship here that our tau xy squared all over 2g is going to be equal to that strain energy density, our value for U, if our values for our tau xy are within that proportional limit. So now that we have this relationship for our strain energy density, our lowercase u, from our equation 11.17 in our textbook, we can find our total strain energy from equation 11.18, where our capital U, or our total strain energy, is equal to the integral of our strain energy density dV. So we can plug in our relationship that we see here from our equation 11.17, where our strain energy density is equal to our tau xy squared all over 2g. Take this, plug this in for our value for U right there, and we end up with what we see here from our equation 11.18. So our total strain energy is equal to the integral of tau xy squared all over 2g dV. So now let's consider the case where we have strain energy in torsion. So if we take a look at this shaft in our diagram here, we have a prismatic shaft subject to torque right here. We can see our T and our T prime has some length L here. So if we call this our shaft AB of circular cross section of length L, subjected to one or several twisting couples, what we can do now is take a look at our polar moment of inertia, our value for J, for the cross section located at whatever distance we are along our shaft at some point, what we'll call X there. So with this here, we have this relationship that our tau xy, or our shear stress, is equal to our torque, there's our torque right here, times rho all over our polar moment of inertia J. So with this relationship, for our shearing stresses, we come over here to our equation 11.18, and for a shaft subject to this torsional load, we see we have this tau xy squared right here. So we now have this relationship that we can plug in relative to our torque and our polar moment of inertia. We plug that into this equation here, and what we end up with is we have now the integral of t squared, our torque squared, times rho squared, all over this 2g times j, our polar moment of inertia squared, dv. Now, similar to what we've done before, we can now set our dv here equal to this dA dx. So again, we can separate this out into two separate integrals where we have now a double integral, one from 0 to L and one over our area. We'll separate this out, and what we have now is we can separate this out over our area here, and this portion of our t squared over 2g j squared will be with respect to x. So we can now say we separate that into two different integrals. This is u is equal to our integral from 0 to L of t squared all over 2g j squared times the integral over a of our rho squared dA dx. So we can do out our math here, do out these integrals, and we end up with is what we see in our equation 11.19 in our textbook. So our u is equal to our integral from 0 to L of our torque squared all over 2gj dx. Now for the case that we see here where we actually have a uniform shaft, we can simplify this down, and we see we have our equation 11.20 in our textbook for this uniform shaft, that u is equal to t squared L all over 2gj. But again, this is only for the uniform shaft that we see in this diagram here. So now in our previous section, we determined our strain energy for a body in a state of uniaxial stress as well as in a plane shearing stress. So what now if we want to figure out this strain energy for a general state of stress? So for our general state of stress, we have the following relationship that we see here given by our lowercase u for our strain energy density. So what we want to recall with this here is that a body in general state of stress is characterized by these 6 different components: our sigma x, sigma y, sigma z, tau xy, tau yz, and tau zx. These 6 components are also shown down here in this diagram on the right in 3D, where this is our x-axis, our y-axis, and our z-axis there. So our total strain energy density is going to include all 6 of these stress components as shown here in this equation for our u, our strain energy density here. Now with respect to our principal axes for an elastic isotropic body, for that case right there, we have this relationship out here for our strain energy density equation. Well, this is now 1 over 2e, where e is our modular elasticity, times now our sigma a squared plus sigma b squared plus our sigma c squared minus 2 nu times now sigma a times sigma b plus sigma b times sigma c plus sigma c times sigma a right there. So this is our equation right there with respect to our principal axes for an elastic isotropic body. And then we simplify this down, and this is simply saying that this is equal to our strain energy density sub v plus sub d right there, where we break these two down. What is our u sub v and our u sub d? Well, our u sub v, this is going to be our strain energy density due to volume change, and our u sub d is going to be our strain energy density due to distortion, and these are given by these two relationships shown here, where our u sub v right here is equal to 1 minus 2 nu all over 6e times that sigma a plus sigma b plus sigma c quantity squared, and our u sub d due to distortion here is going to be 1 over 12g times now our sigma a minus sigma b squared plus sigma b minus sigma c squared plus sigma c minus sigma a squared. Now this is going to be the basis for our maximum distortion energy failure criteria. We have the relationship here that this u sub d from our equation 11.29 up here must be less than our u sub d sub y, which is equal to our sigma sub y squared all over 6g for a tensile specimen. So now let's take some of that theory and governing equations we saw within this module and apply them to a sample problem. So let's take a look here at our sample problem 11.2. So there's going to be 2 parts to this problem. In part A, they're asking us to take into account only the effect of the normal stresses due to bending and then determine the strain energy for the prismatic beam AB that we see down below here for the loading that's shown. So we can see we have a loading here at P, we can see supports here at A and B, we have the total length L, we have the distance to our load at point D of A, and from D over to our point B, we have this distance here, lowercase b. So that's part A. Now for part B, what they want us to do is evaluate the strain energy, knowing now if they give us information on this beam that it's a W10 by 45 beam, and they tell us values now for our load, P is equal to 40 kips, this length L is equal to 12 feet, this distance A here is 3 feet, distance B here is 9 feet, which makes sense because our 3 plus our 9 would be equal to total length 12 right there, and they also tell us that our modular elasticity for this beam is equal to 29 times 10 to the 6 psi. So I'm going to solve this out into two different parts, a part A and our part B. So as we begin our solution, the first thing we want to do is create our setup page, write down all of our given information and everything they've asked us to solve for. So now we create that setup page as the first page of our solution to this problem. So in our setup page, we have the name of the problem. This is sample 11.2. I've redrawn out my diagram over here. I also have my given information. So within my given information, I know this is a prismatic beam from A to B, and it's a W10 by 45 prismatic beam. Now I have all of my variables. So for these variables, I want to have 4 different things. I want to have the variable name, I want to have the numeric value, I want to have my units, and I also want to have how it relates to my problem. So for each of these, I have that same thing. So my load, P, is equal to 40 kips. So P is my variable, load is how it relates to my problem, 40 is my numerical value, kips are my units. Do the same thing for all of my other variables. So I have my length L is equal to 12 feet. I have my length from A to D, so this length right here, which is my A is equal to 3 feet. I have my length from D to B, which is my lowercase b here, which is equal to 9 feet. And I have my modular elasticity, E is equal to 29 times 10 to the 6 in units of PSI. So now that I have all my given information there, the next thing I want to do is write down what they're asking me to solve for. So in my find section, I have 2 parts, part A and part B. In part A, they're asking me to find the strain energy for the loading shown, but take into account only the normal stresses due to bending. And this is all going to be in terms of variables. But for part B, they want us to then find the strain energy, knowing now that we have this W10 by 45 prismatic beam, and now we have numeric values for my P, my L, my A, my B, and my E, and we can plug those in and solve for those based upon those given numeric values, which we've lifted up here in our given section. So now that we've had the opportunity to read through that problem statement, understand everything they've given us, what they're asking us to solve for, and create that setup page that we can reference back to, we can now actually begin our solution. So for our solution, we want to break this down into different parts. There's a part A and a part B to this problem. Let's solve those individually. So first, let's solve for our part A, which we're looking for our strain energy. So for this here, what I want to do first is create my free body diagram and my chosen coordinate system. So I'm going to go with the standard X positive to the right, Y positive going up, draw my free body diagram. I have my beam here, AB. I have my reactionary force here, RA, and my reactionary force at B, R sub B here. I have my load P acting at this point D here. I know my distance from A to P is this lowercase a, and from D to B is this lowercase b here. So with this free body diagram, I'm going to do my equilibrium equation. So let's take a look at my forces in my y direction. Summation of forces in my y direction are equal to 0. So what are my forces acting in my y direction? And again, pay attention to sign convention according to this coordinate system here. So I can say, well, summation of forces in my y direction, I have a positive r sub a going up in my positive y direction. I have a negative p going down in my negative y direction right there. And I have a positive r sub b. So these are all equal to 0. I can rearrange this and I can say r sub a plus r sub b, my two reactionary forces added together, are equal to my load P. So with this here, I have one equation and two unknowns within this here, because I do know my P, even though I haven't plugged in my numeric values for part A of this problem. This is a known value of P. We're going to solve for it in terms of P there. So my two unknowns are my reactionary force R sub A and R sub B. So with that there, I'm going to need another set of equations to relate these together. So what I'm going to do is take the summation of my moments. So I'm going to do the summation of my moments about my point A over here. Let's say, okay, summation of moments is equal to 0 for my equilibrium analysis. So what are my moments acting about point A? Well, I'm going to have this value of P times its perpendicular distance A here, and that's going clockwise, so it's a negative PA plus, I'm going to have my R sub B times its distance, which is A plus B, or L, depending on how we're looking at this here. So my second one was R sub B times that distance going back to my point A there, and this is all equal to 0. Now, if I left it in terms of my A and B distance right here, I have that PA is equal to RBA plus my RBB. Or if I plug those in right here for my AB is equal to L, I can change that back in and rearrange this equation for summation of moments and my equilibrium equation. So I look over here now, I have these two equations, two relationships. I can say I have two equations now and two unknowns. My knowns, which I have here because in terms of variable, I want to write this out. My knowns are P, A, B, and L. My unknowns are my reactionary forces R sub A and R sub B. I have two equations. My equation 1 that I've labeled here is P is equal to the RA plus RB. And for my equation 2, now when I plug in for L rather than A and B, I have that P is equal to my R sub B times that length L all over my distance A there. So I can solve these two, so I can solve equation number 2 here for my R sub B. So I do that there and I say, well, PA is equal to R sub B times my L there. All I've done is multiplied my A over to the other side. So then I can rearrange that and I can say that my R sub B, when I divide by L on both sides, is equal to my PA over L. So now I have a relationship in terms of PA and L, which I go back up here, PA and L are all known values for my reactionary force, which was one of my unknowns at B. So now I can take this relationship here and I can plug this back into equation 1 for my R sub B. So if I plug that back in, my equation 1 was P is equal to R sub A plus my R sub B. So P now, when I plug in for my R sub B with this relationship here, is R sub A plus now my PA over L. So I can rearrange that and solve that for R sub A. My R sub A is equal to P minus PA over L. So I can simplify this down. And when I do that there, I recall the relationship that A plus B is equal to L. I can solve this for B. So B is equal to L minus A. So in this relationship here now that I've solved for my R sub A, where I have P minus P A over L, I can multiply P by L over L, which is 1. So if I multiply this by 1, that's fine. We're allowed to do that little math trick there. So RA is equal to P times L over L minus PA all over L. Now with this relationship here, I can pull out a P. I see I have a common P on the top right here. I pull that P out, and I'm left with now that RA is equal to P times my L over A all over L. Well, I recall now this L over A right here is approximately equal to B from this relationship shown above there. So I can plug that in, and now I say that my R sub A is equal to P times B over L, so my R sub A is equal to PB over L. So a couple little tricks there. There's multiple ways that we can do this, and this is a little bit tricky because we haven't plugged in our numerical values. We're solving this in terms of our variable names here. But now we do have an expression for RA and RB in terms of our known variables for our part A of our problem. So for our next step in our solution, we're going to do some modeling here. So we'll draw out our free body diagram and our moment diagrams. So I redraw that same free body diagram I saw before. There's my reactionary force A, reactionary force B, and our load P there. And we have our distances in terms of our variables, our A and our B, and our P is located at this point D right there. So from that, I want to draw out my moment diagram directly below that there. So I draw that out. You can see now I'm going to have some moment 1 at some distance x away from our distance here at point A, and I'm going to have some moment 2 here, some distance v from the end of the beam at point B here, and we can see I have our maximum moment right there where our load is located at our point D. So within this here, I want to break this down for our M1 and our M2 and draw our free body diagram. So let's draw our free body diagram for the left side of this right here from A to that point D. Well, we're going to have now a reactionary force acting at point A that we can see from our free body diagram there, and out here where we section this here at some distance x away, we're going to have M1 and the shear force V1. Now similarly over here on our right hand side, if we draw our section over here and we have this distance now over here, this V distance, we're going to have our M2 and our V2 at the end of the beam where we section it there. Over at the right at their fixed end here, we're going to have a reactionary force R sub B right there. So these are our two free body diagrams for the two ends of our beam. So with these free body diagrams, so our free body diagram from A to D and our free body diagram from B to D, which I'm redrawn over here for us to reference, what we're going to do now is our summation of moments about that point D for both from the section from A to D and our section from B to D. So let's take a look first at our section from A to D in this free body diagram here. And with this here, we can say, okay, summation of moments about D is equal to 0 for equilibrium. What are those moments? Well, we have this moment M1 from our free body diagram there going counterclockwise, so that's positive. Then we also have this moment from our reactionary force RA times the distance x right there, which is going clockwise, which is negative. So M1 minus our RAX is equal to 0. Rearrange that and we can say M1 is equal to RAX. Well, with this here, we have a value for RA that we solved for previously, and this is equal to PB over L. So we can plug that into our RA. What we end up with now is this expression here that M1 is equal to PB over L times X. So now let's do the same thing for our free body diagram on our right-hand side over here from B to D over here. So from B to D, we have the summation of moments about that D as well again. What are those moments? Well, we have this M2 now, and our M2 you can see is going clockwise. So this is a negative value here. Now going counterclockwise, we have RB, a reactionary force, times that distance V right there. So that's a positive RBV. This is equal to 0 for equilibrium. Rearrange this. M2 is equal to RBV. Now we have an expression here that we saw for earlier that RB is equal to our PA over L. So we can plug that in for our R sub B. And what we find now is we have M2 is equal to PA over L times V. So now we can go back to our problem statement, our initial setup page, to double check what they'd actually asked us to solve for in the problem. So recall when we look back there that they were looking for our strain energy. Now for our strain energy, we have the relationship that our strain energy is equal to our U at AD plus our U at BD. So we can solve for that separately for each of those sections and add those two strain energies together to get our total strain energy. So where we can find U from our equation 11.15 in our textbook, where U is equal to our integral from 0 to L of our moment squared all over 2EI dx. So this is our general equation we're going to do here. We'll separate this out for each individual section. So our U from A to D is going to be equal to our integral from 0 to A, that's our distance there, of our M1, our moment 1 squared all over 2EI dx. And for U sub BD, for that section there, it's the integral from 0 to B, where that's our length of this guy here, of our M2 now squared all over 2EI dV. So pay attention, this is with respect to x, this is with respect to v, this is dealing with our m1, this is dealing with our m2, and our limits of integration correspond correctly as well. So now we go back to this equation here saying we can add this together for our total strain energy, so our u is going to be equal to the summation of both these integrals here, so our integral from 0 to a of our m1 squared all over 2EI dx, plus our integral from 0 to b of m2 squared all over 2EI dv, where we have now these values we've just solved for m1 and m2, so we can plug in for m1 this relationship here, and we can plug in for m2 this relationship right there. So that's the next step, is to go ahead and plug these in. So when we plug in for our M1 and our M2, we have the relationship here that our total strain energy is equal to the integral from 0 to A. We plug in for that M1. Now on the top we have our PB over L x squared all over 2EI dx, plus on the right side, integral from 0 to B of, now when we plug in for M2, this is PA over L V squared all over 2EI dV. Now from here what we want to do is pull out our constants in front of our integral there. So we pull out our constants, we realize that we have our 1 over 2EI and our P squared over L squared as constants right there for both of those integrals. So we'll pull those out front, create our square brackets here, and now inside of each one of these, we separately, in front of our first integral, we have our b squared as our constant, and our second one on the right side, we have our a squared as our constant. So this is going to be b squared times the integral from 0 to a of x squared dx, plus a squared times our integral from 0 to b of v squared dv. Those are pretty straightforward integrals to do, so we do this out here. So this would be our b squared times the integral from 0 to a of x squared dx becomes 1/3 x squared evaluated from 0 to a, and our integral from 0 to b of v squared dv becomes 1/3 v squared evaluated from 0 to b. We plug in those limits, and we end up with now is our total strain energy is equal to, with our constants out front, 1 over 2EI times p squared over L squared times, now in brackets here, our b squared times that a squared over 3 when we plug in from 0 to a there, plus now our a squared, that's our constant out front there, and we do that integral out there. This is now plug in our v with our 0 to b, which is going to be b cubed over 3. So we have this, we can combine these now that our total strain energy is equal to p squared, a squared, b squared all over now 6EIL squared times our a plus b, where our a plus b is our L. Plug that in as L, we see the L cancels with the squared there. What we end up with now on the bottom here is our total strain energy U is equal to P squared, A squared, B squared, all over 6EIL. So now that gave us our answer to part A of the problem. We need to find for the strain energy in terms of the variables. Now for part B, they give us numeric values, and they tell us that we're dealing with a W1045 rolled steel shape for our beam there, and we know that our P is equal to 40 kips, our A is equal to 3 feet or 36 inches I'm converting to, B is equal to 9 feet or 108 inches, L is equal to 12 feet or 144 inches, and our E is equal to 29 times 10 to the 6th PSI or 29 times 10 to the 3rd KSI, and our I is 248 inches to the 4th. This is something we can look up from our Appendix E that we'll take a look at right now. Now, before we get to that, I do want to mention that sometimes it is helpful to do this unit conversion right here at the beginning of each of these sections so you can quickly reference back and don't need to worry about doing those conversions within your solution in our general equations. So moving on to our Appendix E, this is where we get our value for I for this beam. So this is a W10 by 45. So we come down here and we go over here. So our I sub X is what we're looking at here based upon this right here. We can see this is our X we're looking at across this axis here. So this is going to be our axis XX right there. So I sub X is in inches to the fourth for our units right there. So this is going to be our 248. So that's where we got that value from. It's from this Appendix E for our W shapes, our wide flange shapes, and the properties of our rolled steel. So with that given information from our problem statement that we see here, along with this value for I that we've just determined from our Appendix E, we can now start our solution for our Part B. We start plugging in these values. So we have this relationship from Part A that our strain energy U is equal to our P squared, A squared, B squared, all over 6EIL. So now we can plug in those values here, and we find that our strain energy U is equal to, plug in for P is 40 kips squared, plug in for A, which is 36 inches, that's squared, plug in for B of 108 inches, all divided by now here my 6 times my modular elasticity times that value for I times now over here my value for L, it's 144 inches. We can plug that all in. We find that U is equal to 3.89 in units of inches times kips. Now a couple things I want to mention here. One, we can see why it was beneficial to do that conversion to inches up above here. Then we can straightforward plug into that general equation, which leads to the next thing I want to talk about. Now I know Part A was a little bit confusing, and you may be asking yourself the question, well, if I have these numeric values, why am I taking all this time doing these manipulations, rearrangements, and simplifications to get down to this general equation for my strain energy for this particular problem, for this beam right here? Well, one good reason why we can do this is because once we have this here and take that extra time to find this in general form, if these values were changing, if there's a design process and you wanted to play around with different values for A, different values for B, different length, different materials, you're going to have different values here now for your E and potentially your I as well. Maybe you even want to try different styles, different shapes here for your beam, then you can just plug those in as variables within MATLAB, within Excel, whatever you may be using, even Python, plug those in, and you can rotate those through until you get the values that you want. Or maybe you weren't sure what the max load could be, so you left that as a blank variable, and you knew what in your specifications your U was. You could play around with this within MATLAB or Excel and spit out what that load should be. So having this general equation, taking the time to make that and plugging it in, it's quick and easy to pop in these known values there and play with them to get your design criteria just right. So that's the benefit of doing that out like we did in Part A and then just plugging in. So we did this in one slide. Quick and easy, plug in one little equation here to get our value here based on those numeric values. So having it in general form can be very beneficial.